Good morning everyone. This is Senthilnath from GeoConsult Asia, Singapore. I'm happy and honored to be the first speaker of this ITA YM webinar series. In this episode of this series, I'm going to present a topic on the effect of new TBM tunnels on the existing subway tunnels. I'm going to give some case study examples. To start with the presentation, I would like to present what is the context of urban infrastructure, urban underground infrastructure in Singapore. For example, in Singapore, at the surface we have all the surface utilities, and below we have the urban and road infrastructure, and further down we have the urban rail infrastructure, and further down we have the deep sewer system, this utilities like deep sewer system, water supply system, and stormwater drainage system. And further down we also have, in Singapore specifically, we have a power backbone infrastructure system. Even further down, as you can see, we also have an infrastructure for ammunition facilities, storage of ammunition facilities, also for petrochemical storage. So we have this layered system of underground. So with this layered system of underground infrastructure, we have a different, obviously we have problems like the interaction between one tunnel to the new tunnels. So in this presentation, what I'm going to do is I'll just give you an overview of urban tunneling using TBM, and then what are the impact assessment methods available, just an overview, and then how we, when during construction, when it is being constructed, how we are going to, how we control the settlements. Is it codal specification or is it a performance specification? And then we are giving some case studies, and then I will discuss about some control measures which we are adopted for this project in Singapore. So in general, urban tunneling, as you all know, the main aim is to limit settlements and to prevent any form of collapse. So we want to limit the settlements, we want to avoid any form of collapse. So for this solution, we use a closed TBM, which is supposed to be controlling the settlements in a very controlled manner. So we have different types of closed TBM excavation. There are three types of shields used in Singapore, like compressor, slurry shield, and EPBC. And apart from the phase extrusion, this settlements due to phase extrusion, we also have some volume or ground loss due to shield, or excavation also due to shield loss. But the main idea is, of all the things, of all the aspects contributing to the settlements, at the end we want to calculate what is the total impact of all this kind of settlements at the surface level. So we have certain models available, like for assessment of greenfield settlements, we have prediction models by PEC, where we use the Gaussian distribution to estimate the settlements at the ground level, which is very well implemented and very well documented to be very successful in all the projects. But this is for greenfield. So further down, we have also developed the prediction models for impact on piles, which can be used to estimate the tunneling induced horizontal displacements and strains. Based on these two methods, Berlin et al. Further extended this estimation method. The earlier methods were only in the cross section, but also this Berlin et al. Extended for the longitudinal section, which enabled us to estimate the settlements in a 3D distribution form. So we can use these methods to estimate the surface as well as subsurface. This is straightforward when we have a very idealistic scenario. But however, when the tunnel configuration is bit complex, the complete assessment is different. In cases where we have a complex tunnel configuration, for example, when there is TBM crossing another existing tunnel, in the plan, when the new tunnel is crossing the existing tunnel at an inclined angle. So in section we can see like this, but in plan it is crossing at an oblique angle. So in such situations, the assessment methods which we have may not be accurate under certain circumstances, because the complete assessment requires to study the impact due to the different position of this new tunnel, and it has a temporal variation. That means the maximum settlement induced to the new tunnel on the existing tunnel will be varying with the tunnel. As you can see on the sections with different time, you can see that the maximum displacement was caused at this point, and after the tunnel has progressed, the final settlement is slightly less. So that means the final distortion is not necessarily the maximum. The final settlement occurred somewhere in between. So which emphasizes the needs of case-to-case study of the exact configuration of the tunnels. So if you want to assess the complex configuration methods, we can go for a detailed study as we have shown in the previous slide, or we can go for an numerical assessment where we are able to simulate mostly the boundary conditions and all the constraints we have in the model. So we can use numerical model for this case. But the next stage is, okay, we have used a simplified model or a numerical model, or we have adopted our simplified model to suit for the configuration. But at the end we get these estimated settlements. When it goes for construction, we need to set certain allowable limits or certain review levels during the construction. So these review levels can be based on certain codal provisions or can be based on performance objectives. Here in our case studies, what we understood is sometimes the allowable limits set by the codal practices are very conservative, but sometimes they are not necessarily conservative, and they are not actually controlling the performance of the structure in concern. So in our case study, we studied to use the performance based objectives as the review levels rather than the codal practice of the codal practice levels. So just to give an example of performance objectives for a railway tunnel, if a new tunnel is crossing an existing railway tunnel, we want to understand what are the maximum performance limits the existing tunnel needs to be adhered to. For example, the new tunnel should not cause any ovalization, should not be causing any squatting in the existing tunnels, or stepping or opening of circle joint. And each of these performance case or performance criteria is studied to assess what is the allowable ovalization. That means if the new tunnel is crossing, the existing tunnel should not ovalize more than certain limit. This is calculated based on the segment design which was used in the existing tunnel, and we can how much extra moment, what is the extra moment capacity it can still take. So based on these criteria, we can calculate for ovalization and squat, and similarly for stepping and opening of circle joints of the tunnel lining, we can calculate based on the existing thickness, hydrophilic strips, and all the waterproofing measures which has been used in the existing tunnels. We have calculated what are the allowable limits for each of these performance objectives. So further down, for the operational, in the last slide I showed the performance objectives from a structural performance point of view. In this slide I am showing the performance objectives from an operational point of view. So the existing tunnels should be able to still operate while the new tunnel is undercrossing or overcrossing it. So for our case study, we have taken these performance objective as the limiting criteria, that the geometry of, that is the alignment of vertical and horizontal alignment should be within this certain limit, which is based on the operational criteria of the railway tunnels at different speed levels, and it should also obviously the movement in the existing tunnel should not cause so much displacement that there is no structural gauge clearance for the existing trains to pass through the existing tunnels. So these are performance objectives from an operational point of view. So just to summarize these performance objectives, I will be trying to explain in terms of 3 case studies very briefly. So the first case study is TBM tunnel overcrossing a live railway tunnel. In this case study, we have 3 sets of railway tunnels. This is the northeast line in Singapore, and this is the existing east-west line in Singapore, and this is the proposed new tunnel. This is Thomson line. So one tunnel is going towards the eastbound, one tunnel is going towards the westbound. So totally we have 6 tunnels in this configuration. This is a 3D model, you can see here. So our tunnel, which is the new tunnel, is Thomson line. These 2 lines are being constructed. So we need to make sure these 2 tunnels are not causing any undue stress or undue movements on the existing tunnel. These two. So since these 2 tunnels are quite old, from a Singapore perspective, it's quite old, from 20 to 30 years old, and so here we are overcrossing this tunnel, and the vertical clearance is as less as 3 meters. So which could possibly cause some type of heaving. So we studied in detail in a 3D model, and this as you can see here, this is the soil profile here. Probably it's not so clear, but here we have fill followed by Jurong formation, which is basically sedimentary rock in various degrees of weathering. The ground is relatively good. The main concern was because of the close clearance between the existing tunnels and the new tunnels, and we expected some kind of heave. And so we assessed the problem, and we calculate what is the maximum allowable heave and what is the maximum allowable horizontal displacement which the new tunnel is going to cause on the existing tunnel. And in addition, we also calculate, because of this heave and because of this displacement in both in vertical and horizontal, we calculate what is the additional bending moment or additional forces going to be induced in the existing tunnels. And it was compared with the from the performance objective in mind, rather than as fixed codal provision. In Singapore, the fixed codal provision is that the tunnel should not displace more than 15 mm. But in this case, we have used performance objective as our limiting criteria, or as a review level, rather than as a codal provision. And this criteria for vertical alignment, horizontal alignment, we calculate to be based on the operational criteria of the railway authority. We calculate it to be 5 mm and 6 mm, and our estimated movement was much less than that. The next case study is the case where TBM tunnel is undercrossing a live railway track. This is quite interesting, where this is the existing tunnel, this east-west line built in late 90s, and this is the new tunnels. So the vertical clearance is around 6 meter, which is 1 times the diameter of the tunnel. All the tunnels are of around 6 meter diameter here, and the more challenging thing was, it was running just below the existing tunnel for a continuously parallelly for a distance of around 300 meters. The minimum horizontal offset between the center of this existing tunnel and the new tunnel is around 4 meter. The vertical clearance, as I said, is only 6 meter. Since we have to assess all along the drive from the point where it starts going parallelly below it, we had taken multiple cross sections to assess the impact on throughout the section where they are going parallel. In the next slide, so for each section, we have done an assessment to estimate the impact on the new tunnels on the existing tunnels. We have tried to assess what is the vertical displacements, horizontal displacement, vertical strains and horizontal strains. Since this is it is a 2D problem, it need not be done in a 3D model. So we have done multiple sections, and then we compile in the next few slides. I will be showing that we have compiled and to show what is the impact throughout the alignment. So we have tried to do an assessment using an empirical model, then compared with the numerical model, which seem to really match very well. And then after we have done for each section, so one section we have done a set of analysis. So it's similarly we do for each section or a set of analysis, and we see how each criteria is matching along the alignment. For example, in this chart, I am only comparing the total displacements, that is vertical movement and horizontal movement of the existing tunnel. So these two, the purple line shows the displacements of the eastbound tunnel, and the green line shows the displacements of the westbound tunnel. As you can see, at certain locations the tunnels are not exceeding the allowable limits, but at certain stretches, because of the varying soil conditions and different TBM operating parameters, are exceeding this allowable limit. So we know that these are the stretches where it is very critical, and we need to further assess from a performance objective to clearly understand whether it is really exceeding our performance criteria or not. So in the next slide, I'll just summarize the similar exercise which was done for all the other performance objectives, apart from the displacement of the existing tunnel itself. So we listed down, these are the criteria which needs to be assessed very critically to understand, to see that the new tunnels are not causing any undue stress on the existing tunnels. And we have set the allowable limits based on the structural strength and the operational criteria of the existing tunnel, and these are the different instruments which are installed to measure those performance objectives. So the next case study is quite interesting, which is different from the other two cases, where we have a TBM tunnel docking just below a station. This was quite challenging. Although this was in quite competent rock, the main challenging aspect was in terms of controlling the allowable water ingress inside this docking location. So the objective here was the two TBM came close together, and they were dismantled and decommissioned without any intermediate shaft, and all this happened below an operating railway station. So it was the gap between these two shield length is a kind of NATM or a shortcut line tunnel. Here in this case study, the main performance objective was not controlled by the settlements, but the performance objectives were controlled by the water ingress or the settlement induced by water ingress. So this slide shows the grout block which was designed around this docking location, and this shows briefly the face log of the location where the TBMs were docked. It was mostly a Jurong formation, which is we call Jurong formation in Singapore, which is basically a sedimentary rock, which is, in this case, it was siltstone and sandstone. And there was, at this docking location, we tried to minimize the water ingress as low as 20 liters per minute because of the systematic grouting which was done. But coming from a settlement assessment or the performance assessment of the structure itself, it was, as I said, it was not much governed by the volume loss due to tunneling, but it was more due to settlement. It was more due to the settlement caused due to water drawdown. So what we have done is done a systematic 3D numerical model for the flow analysis to estimate what is the allowable water ingress for a period of 3 months, to see how much water can be allowed during this mine tunnel construction, so that it is not causing any displacement to the structure. So in this structure, to make sure the structure is not unduly stressed, we try to model the whole structure in our 3D model, and we assess the additional bending moment and forces caused due to this operation. So we said that the maximum allowable limit was in the range of 80 to 90 liters per minute for a duration of 3 months. So far we have seen 3 case studies where we have tried to see what is the impact due to the new tunnels on the existing tunnels. We try to assess what is the additional stresses, displacements caused on the existing tunnels. But from an operational point of view, when the contractor is given with this review levels and he has to adhere to certain amount of displacements or certain amount of water ingress or certain amount of stresses on the existing tunnels, he has to do certain control measures. So here I try to briefly explain the different control measures which we adopted for our projects. Just to be clear, these are the control measures from an operational point of view, not from a design point of view. So basically all the operational control measures can be classified into three groups. One is the improvement of ground, which can be improvement of strength or permeability, or it can be conditioning of the material inside the TBM, and it can be back pressure at the end of the screw conveyor. I will try to explain these three control measures using an nomogram from Ananyusu Kovari, where this nomogram clearly shows what is the support pressure required for different cohesion values and different head levels. When we have, as we know, the total phase pressure applied at the TBM will be a combination of effective phase pressure plus the water head in the chamber. So this is the water head in the chamber. This is the total water level we have in the water level ahead of the TBM. So the total effective total phase pressure to be applied for the TBM drive is the sum of effective phase pressure plus the water head. In next slide, when we say that we are improving the ground, what we are trying to do is we are increasing the cohesion. That is, when we are increasing the strength of the soil, that means we are increasing the cohesion. So we are going from this, for example, when we have a cohesion of 20 kPa and certain water head, say for example water head difference is 50 meters. So from this point, after we increase the cohesion, we go from here to here. So the effective pressure is, we bring it down from here to here. This is just for illustration. It may not be the this difference is not scalable, but this is just for illustration. So similarly, in the next slide, when we say that we are decreasing the permeability, that means we are decreasing the water head difference. This difference H0 minus H, we are decreasing this head difference from 50, we are going down to 15. So the effective support pressure is brought down from say around more than 200 to around 50 kPa only. The second group of ground improvement is conditioning. So what we achieve by conditioning is we are trying to improve the properties of the excavated materials in the excavation chamber and the screw conveyor. By conditioning these material using various commercially available additives, we are giving the soil inside this excavation chamber the ability to dispense the pressure within this limit. If there is no proper conditioning agent, then the soil in the excavation chamber will not be able to resist this level of this difference in the pressure between the excavation chamber and at the end of the screw conveyor. The other way, that is the third method, is to apply a back pressure at the end of the screw conveyor. By applying this back pressure, what we are trying to do is, we have not reduced, we have tried to reduce certain head here, and we are not going to zero here because we are putting some pressure. So at the end, when we see our H minus H0 is also reduced. So in both the cases where we are using conditioning agent or where we are using this back pressure method, we are trying to reduce the H minus H0. And as I shown in the earlier slides, that by reducing the H minus H0 in the nomogram, we have seen that we are trying to bring down the effective support pressure. But how is the effective support pressure going to help is the question now. When we bring down the effective support pressure, our total support pressure is also coming down. And when our total phase pressure is less, we have less wear and tear of the tools. That means we have to stop the TBM less frequently, and that means we will have a smoother drive, and there is a less fluctuation of the phase pressure. If the phase pressure is quite high during the operation, there will be a very high fluctuation of the target phase pressure. So by bringing down the total support pressure, we are reducing the fluctuation in the phase pressure. We are also trying to reduce the wear and tear of the tools. So in summary, so far we have seen that there are different methods to assess the impact of the new tunnels on the existing tunnels, and we have seen there are some limitations of the existing empirical models because of different temporal and geometrical configuration, and if they are well adopted and they are modified to suit our requirements, they can give reliable results. We also demonstrated using the 3D numerical model that if used properly, they can give a very good prediction of the associated risk and forces on the existing structures. So here in this presentation, I tried to cover these points, and I hope it was informative. I thank ITAYM and all the listeners for listening to me very patiently. Thank you.